Welcome to my workshop. I'm Jim. Today I want to share with you what I've learned about using the 555 timer chip in continuous mode. If you're only interested in the equations which determine the timing, then skip ahead to 11 minutes and 40 seconds into the video. Otherwise, let's get started. I've already prepared a small breadboard. I've wired up 4 similar circuits. 1, 2, 3, 4, each with its own 555 chip. I will now plug in the battery, which is a 2S LiPo battery with a nominal voltage of 7.4 volts. I've connected an LED to the output pin of each of the chips to show the waveforms. You can see the LEDs pulse on and off in regular repeating cycles. You can also see that each 5.5 chip is generating a square wave, but that the square waves differ in the length of the pulses and in the length of time between the pulses. In each of these circuits, the timing of the square wave is determined by 2 resistors and a capacitor. For example, these are the 2 resistors and the capacitor for this chip. The main task when using 555 timer chips is to choose values for these 3 external components which will produce the desired stream of pulses. I'm now going to put the breadboard aside for a minute and start to describe what's going on. A 555 timer chip is a small 8-pin IC. IC stands for integrated circuit. An integrated circuit is a circuit containing a large number of very small resistors, capacitors, and transistors, all burned onto a tiny circuit board and then molded inside a plastic or ceramic case. Like many ICs, the 555 chip comes in a dual inline package. It has a row of pins along each side, hence the word dual. The pins along each side are arranged in a straight line, rather than an arc or a circle, hence the word inline. For short, this style of package is called a dip chip, D-I-P. Since the 555 chip has 8 pins in total, we would call this a dip 8. 555 timer chips come in other styles of packages as well, but this one is the most useful for breadboarding and printed circuit boards. Pin number 1 is always at a corner, and the pins are always numbered in the counterclockwise direction around the chip, as seen from above. Pins 1 to 4 run down one side, and pins 5 through 8 run up the other side in the opposite direction. How do you tell which corner is pin 1? There are 2 ways. A small round dimple or depression will be molded into the case right above pin 1. A small semicircular notch will be molded into the case on the end which has pin 1. All dip chips have one or both of these features for locating pin 1. The data sheet for any IC will include a diagram called a pinout. This diagram always shows the top view, looking down onto the chip from above. The pinout shows the number of each pin and includes a word or abbreviation which identifies its function. This is the pinout for the 555 timer with its 8 pins. Pin 1 is the ground pin. When a 555 chip is wired up, this pin will be connected to the circuit ground. Pin 8 is VCC, to which the power supply will be connected. The abbreviations for pin 2 through 7 are short for trigger, output, reset, a control voltage, threshold, and discharge. The 555 chip is shown on a schematic as a rectangle. A schematic is intended to help a person understand what the circuit does, not what it looks like. Therefore, it's not necessary for the pins to be drawn in the same order as they are arranged physically around the chip. It's usual for the ground pin, which is pin 1 here, to be shown at the bottom, like this. The schematic will show this pin connected to the circuit ground. The VCC pin is usually drawn at the top. In the breadboarded circuit, VCC is connected to the battery. The symbol VCC is often used to represent positive supply voltage. Sometimes the symbol VDD is used instead of VCC. These subscripts, CC and DD, are holdovers from the olden days when radios were powered by C and D batteries. You may also see V plus used for the positive supply voltage. Schematics are usually drawn so that signals pass from left to right, with inputs coming in on the left and outputs going out towards the right. In our schematic, then, I'll draw the output pin, which is pin number 3, on the right-hand side of the chip. When the 555 chip operates in continuous mode, the voltage on this pin 3 will rise and fall in a continuous square wave. When the output waveform is in the low state, or off, the voltage at pin 3 will be at ground, or 0 volts. I've highlighted this part of the square wave in red. When the output waveform is high, or on, the voltage will be the voltage at the VCC pin. I've highlighted this in blue. Since the breadboard's power supply is 7.4 volts, the voltage at the output pin is going to alternate between 0 and 7.4 volts. 3 of the remaining pins are used to control the timing of the square wave. In the schematic, I will draw those 3 pins on the left-hand side like this. The 3 pins are the discharge, trigger, and threshold pins. 3 external components are used to determine the timing. One resistor, which I will call RA, is connected from the positive power supply to the discharge pin, pin 7. A second resistor, which I'll call RB, is connected between RA and pin 2, the trigger pin. Pin 2 is then wired directly to pin 6, the threshold pin. Finally, a capacitor C is connected between RB and ground. The values of these 3 components set the duration and spacing of the pulses. In a minute, I'll describe the relationship. 2 pins remain. Pin 4 is the reset pin. This is a specialized control pin. It's called a control pin because it changes or controls what the chip is supposed to do. The reset pin is active low. Active low is a defined term which means that this pin will cause something to happen only if the voltage applied here is low, or 0. If the voltage applied here is high, or 7.4 volts in our circuit, then this pin will do nothing. The reset pin on the 555 chip is hardly ever used, and it isn't used in our breadboarded circuits. To disable the reset pin and prevent it from doing anything, all we need to do is connect it to the positive supply voltage like this. Just so you know, the reset pin can be used to stop the 555 chip from generating the square wave output. Whenever the reset pin is grounded, the output voltage at pin 3 will be a flat line at 0 volts. The final pin is the control voltage. This is another control pin which is hardly ever used. It can be used to override the timing set by the 2 resistors RA and RB and capacitor C. To disable the control voltage function and prevent it from having any impact, pin 5 is connected to ground through a small capacitor. The value of the capacitor must be 0.01 microfarad or larger, but other than that, its exact value is not important. Some types of capacitors have polarity. A 0.01 microfarad tantalum capacitor, for example, has a positive side and a negative side. If you use a polarized capacitor at the control voltage pin, then the positive side should be connected to pin 5. If you use a non-polarized capacitor, like a ceramic one, then it doesn't matter which end is which. On the breadboard, I've used LEDs to allow us to see the output voltage. I've wired an LED and a current limiting resistor in series with the LED between the output pin, pin 3, and ground. We want the LED to light up when the output voltage is high. When it's high, the voltage drop over the series combination of the resistor and the LED will be 7.4 volts. Now, we know from a previous tutorial about LEDs that the voltage drop over the LED when it's lit will be almost exactly 2 volts. It follows that the voltage drop over the resistor by itself will be the supply voltage 7.4 volts less that 2 volts, or a net voltage of 5.4 volts. The LED will light up nicely when 5 milliamps of current flows through it. Since they're connected in series, the same 5 milliamps of current will flow through both the resistor and the LED. Since we know the voltage drop over the resistor and the current we want to flow through it, we can use Ohm's law to calculate the necessary resistance. Ohm's law is V equals IR. Voltage equals current times resistance. The equality is preserved if we divide both sides by the current I. Dividing by the current makes sense because it then allows us to cancel out the current which appears on both the top and the bottom of the term on the right-hand side. The right-hand side then reduces to the resistance R, which is what we're trying to calculate. When we plug in the voltage drop of 5.4 volts and the current of 5 milliamps, which is the same as 0.005 amperes, we get a resistance of 1,080 ohms. A standard 1K resistor, or 1,000 ohms, will work perfectly fine here. So, this is the branch containing the LED and the resistor, which will allow us to actually see the pulses in the square wave. Now that we've figured out how all of the chip's pins are wired up, it's time to circle back and describe how the timing is controlled. Setting the timing is a matter of choosing values for the 3 external components inside this red ellipse. I'll start by looking at the length of time during which the square wave is low. This time period is called T off. The formula for T off is this: 0.693 multiplied by the resistance of RB and then multiplied by the capacitance. The resistance and capacitance are stated in ohms and farads, respectively, and the T-off, which is calculated, is given in seconds. Suppose that RB is 4,700 ohms, or 4.7 K, and that capacitor C is 100 microfarads. We would calculate T-off like this. RB is 4,700, and C is 0.0001 farads. Remember that 1 microfarad is 1/1,000,000th of a farad. So 100 microfarads is 0.0001 farads. Carrying out the multiplication gives T-off as 0.33 seconds. That's very close to 1/3 of a second. Now let's look at the length of time during which the square wave is high. This is T-on. T-on has a very similar formula. The only difference is that it is the sum of the 2 resistances, RA and RB, which appears in the formula. Suppose that RA is 4.7 K. This happens to be the same value as RB, but I could have chosen any other arbitrary value. The sum of resistors RA and RB is 4,700 plus 4,700 for a total of 9,400 ohms. Plugging this into the second formula gives T-on as 0.65 seconds, which is very close to 2/3 of a second. The output from this 5-5 timer will therefore be a continuous square wave, which will repeat about every second. It will be high for 2/3 of a second, during which the LED will be on, and then it will be low for 1/3 of a second, during which the LED will be off. I'm showing the breadboard once again. I'm zooming in on the first one of the 4 circuits. I plugged this 555 chip into the breadboard with pin 1 on the lower left-hand side. You can possibly see the notch on this end of the chip. Pin 1 is connected to ground through this black wire. Pin 8 is connected to the 7.4 volt supply by this red wire. Pin 4, the reset, is tied high over here. This is a 0.01 microfarad capacitor, which connects the control voltage pin to ground on this side. This is RA, this is RB. Both of these resistors are 4.7 K. This is capacitor C, which is a 100 microfarad electrolytic capacitor. These orange wires connect the midpoints of these 3 external components to the appropriate pins on the chip. Finally, pin 3, the output pin, is connected to this 1K resistor, which in turn is connected to the positive lead of this LED. As near as I can tell, this LED is flashing exactly as designed, on for 2/3 of a second and off for 1/3 of a second. I want to show next that there's lots of flexibility when it comes to picking the values of the external components. The timing of a square wave is completely defined by two things: the length of the pulses and the length of time between the pulses. These are T on and T off respectively. In other words, to generate a square wave, all we need to know is these two times. On the other hand, we're free to select values for three components: 2 resistors and 1 capacitor. We will find that different combinations of the three components give rise to the very same waveform. Let's look at an example of what this means. We just looked at a circuit where the 2 resistors were 4.7 K and the capacitor was 100 microfarads. T off was 0.33 seconds and T on was 0.65 seconds. What if we increase the values of the resistors by a factor of 10, from 4.7K to 47K? At the same time, let's reduce the value of the capacitor by a factor of 10, from 100 microfarads to only 10 microfarads. When we substitute these new values into the formulas, we find that T on and T off have exactly the same values as before. If you look back at the two formulas, you'll see that both of them have a resistance multiplied by a capacitance. If the resistance is increased by a factor of 10 and the capacitance is reduced by a factor of 10, then the two changes cancel each other out and the times are unchanged. In other words, both of these combinations will generate the same square wave. I'm showing the breadboard once again. This time, I'm zooming in on 2 of the circuits. This circuit on the left is the one we looked at a few moments ago. This one on the right is the same, except the resistors in it are 47K and the capacitor is only 10 microfarads. It'll take a moment to get your bearings. Focus on just one LED first and assess its behavior. Then turn your attention to the other LED and confirm that it's flashing in a similar way. Although the two square waves are the same, they're not synchronous. The two chips are operating independently from each other, and there's no reason why a low to high edge on one of the chips should occur at exactly the same instant as the corresponding rising edge on the other. But there's something else as well. The square waves don't have exactly the same period. They're close, but not exactly the same. The reason is this, that the resistance of a 47K resistor like that is not exactly 47,000 ohms. Resistors and capacitors are manufactured with tolerances. For example, this 100 microfarad capacitor has a tolerance of 20%. Its true value could be anywhere between 80 and 120 microfarads. This 10 microfarad capacitor has a 10% tolerance. Its true value could be anywhere between 9 and 11 microfarads. The resistors, too, have their own tolerances. If we knew the exact value of the external components, then the timing formulas would give us a very accurate result. As it is, the timing of the waveforms can't be known or predicted with any more accuracy than the components themselves. It follows that these two circuits will never operate synchronously. One will always be a little bit faster or slower than the other. I want to talk about the duty cycle of the square wave coming from the timer chip. A duty cycle is the fraction of time during which something is active. Usually it's expressed as a percentage of the total time during which that something is taking place. I've shown here the face plate of an arc welder. The duty cycle is said to be 60%. Although it's not explicitly stated, this is actually the maximum duty cycle which the manufacturer recommends. We can think about welding a joint in a series of intervals. We can weld for a little bit and then stop for a little bit while the welding machine and the joint cool down. If we weld continuously for 30 seconds and then let things cool down for 20 seconds, then the duty cycle is calculated like this. The active time of 30 seconds divided by the total time of 50 seconds. The duty cycle for this particular pass is 60%. We could repeat another pass just like this, with 30 seconds on and 20 seconds off, without overstressing the welding machine. The square wave generated by a 555 timer can be characterized by its duty cycle as well. The T-on and T-off times of the waveform correspond to the active and inactive times of the welder. We can expand the formula for T-on by breaking the sum of resistances Ra and Rb into two separate terms, like this. Then, observe that the term in Rb, which I've highlighted in red, is exactly the same as T-off. Since resistance Ra and capacitance C will always be positive, it must be the case that T-on is greater than T-off. It follows that the duty cycle must always be greater than 50%. Let's calculate the duty cycle for the first circuit we looked at above. That's the one with the 4.7K resistors and the 100 microfarad capacitor. I'll quickly run through the calculations again. T-off is 0.693 multiplied by resistance Rb, which is 4,700 ohms, and then multiplied by the capacitance, which gives 0.33 seconds. Similarly, T-on is 0.693 multiplied by the sum of the two resistances, which is 9,400 ohms, multiplied by the capacitance, which gives 0.65 seconds. The duty cycle is found by dividing the on time, 0.65 seconds, by the total time, which is the sum of T-off and T-on. The result is 66.3%, close to 2/3 of the time. The second circuit we looked at before has the same square wave, and therefore will have the same duty cycle. A natural question to ask is, how close can we get to a 50% duty cycle? It's true that the on time, T-on, must be greater than the off time, T-off, but how close can we get to making them the same? Let's start with the circuit we just looked at to see what we can do. Observe that the only difference between the two formulas is the resistance Ra, and that Ra appears only in one of the formulas. If we could somehow make Ra 0, then the two times would be the same. The smaller we can make Ra, the closer the two times will be. Suppose we reduce Ra from 47K to 1K. That has no effect on the formula for T-off, which remains 0.33 seconds. Note that I've added one more digit of precision and shown the value as 0.326 seconds. The formula for T-on does change. The sum of the two resistors is now 1K plus 47K for a total of 48K. Carrying out the multiplication gives the on time as 0.333 seconds. The new duty cycle is calculated as T-on divided by the sum of T-off and T-on, which gives a duty cycle of 50.5%. I'm showing the breadboard once again. I've wired up the third circuit, as just described, with Ra being a 1K resistor, Rb staying at 47K, and capacitor C as a 10 microfarad capacitor. If this timing circuit is being used to convey information to a human being, then this duty cycle is probably close enough to 50-50. It certainly looks like a 50-50 square wave to me. For some applications, though, 50.5% is still not close enough to 50-50. One could continue to reduce the value of Ra, perhaps to 100 ohms, for example, but there is a practical limit on how small Ra can be. If Ra gets too small with respect to Rb, then the circuit will stop producing a square wave and the output voltage at pin 3 will just be a constant. I'll describe this practical limit later on. Although T-on is always greater than T-off, there is a trick we can use to get short LED pulses. The output square wave produced by our standard 555 timer circuit is this, with the voltage high for more than 1/2 of the cycle. When the voltage on output pin 3 is high, as shown by the red arrows, the LED will be forward biased. Current will flow through the LED and it'll shine. When the output voltage is low, there will be no voltage drop over the LED and it'll be dark. Now let's keep everything the same, but move the LED and its current limiting resistor to the top side of output pin 3. Since we did not change the external components RA, RB, and C, which determine the timing, then the output waveform at pin 3 will be exactly the same as it was before. What will be different this time is that the LED branch will now be forward biased when the voltage on output pin 3 is low. In this condition, the voltage drop, that is the red arrow, will be 7.4 volts. The battery will provide the voltage at the top of the branch, and pin 3 will hold the bottom of the branch at 0. It's during this part of the output waveform that the LED will light up. When the voltage at pin 3 goes high, then there will be no voltage drop over the LED, and it will turn off. All we've done with this little trick is to reposition the LED so that it lights up during that part of the output waveform which we've called T off. Let's see what it looks like in practice. I'm showing the breadboard once again. This is one of the circuits that's on for 2/3 of a second and off for 1/3 of a second. I'm now plugging in a second LED. This is its current limiting resistor, which I'm plugging in with its positive end, top end, wired to the 7.4 volt supply. I'm going to use this yellow wire to connect the output pin to the bottom end of the LED. Good. You can see that the LED is on for 1/3 of a second and off for 2/3 of a second. Notice that there's nothing to prevent us from running both of these LEDs at the same time. Let's work through a design example. Suppose that we've been asked to prepare a circuit which produces a square wave, which is on for 1 second and off for 1/4 second. The task is to calculate the necessary values for the 3 external components. The first step is to make a guess for the capacitance. A bit of experience helps here, but it's not that important. If the guess turns out to be unsuitable, the calculations will point us in the right direction to make a better guess. I've guessed that a 10 microfarad capacitor will do. We've just looked at a couple of circuits whose period was in the neighborhood of 1 second, and a 10 microfarad capacitor worked fine for them. Step 2 is to calculate RB, the resistor in the middle. The starting point is the formula for T off. This is an equality, so we can divide both sides by any number and it will still be an equality. Let's divide both sides by 0.693 times capacitance C. The 0.693 on the top and the bottom can be canceled out. The capacitance C is also on the top and bottom, so it can be canceled out. What's left is resistance RB, which is what we want to calculate. Let's plug in the values we know. T off is 0.25 seconds. The capacitance is 10 microfarads, or 0.00001 farads. Completing the arithmetic gives RB as 36,100 ohms, or 36.1 K. The closest resistor I had in my parts box was 33 K, so that's what I used for RB. Step 3 is to calculate the top resistor, RA. The starting point this time is the formula for T on. Once again, this is an equality and we can divide both sides by any number we want. It makes sense to divide both sides by 0.693 times C, which is the same factor we used in step 2. The 0.693 cancels out, as does the capacitance C. What's left is the sum of resistances RA and RB. Let me show the formula without the intermediate step in the middle. Now let's plug in the values we know. T on is 1 second. The capacitance is 10 microfarads. Completing the arithmetic gives the sum RA plus RB as 144,300 ohms, or 144.3 K. We need to carry out one more step. We need to carry out a subtraction to find resistance RA by itself. If we subtract RB from the sum, we will get RA. The sum is 144.3 K, and RB is 36.1 K, so the subtraction gives us RA as 108.2 K. As an aside, you should note that resistors are not manufactured in arbitrary values. For example, it's not possible to buy a 108.2K resistor. Resistors are made in certain standard values. The closest standard value to 108.2K is 110K, and I used a 110K resistor for RA. It will be very rare that one of your calculations gives the resistance which is a standard value. Almost always you'll have to make do with a resistance which is close, but not exactly the calculated value. The last step is a reality check on the values of the resistances. Suppose our calculations had suggested that RA should be 108 megohms, or 108 million ohms. That's huge, much too large to be practical. We would have to start over again at step 1, assuming a bigger capacitor, which would result in smaller resistances. On the other hand, suppose our calculations had suggested that RB should be 0.001 ohms. That's too small to be practical, and the best remedy would be to start over again assuming a smaller capacitor, which would lead to bigger resistors. The fourth circuit in the breadboard has been wired up to show the design example at work. RA is this 110K resistor. RB is this 33K resistor. The capacitor is 10 microfarads. Since this happens to be a ceramic capacitor, it doesn't matter which end is which when we plug it in. As designed, the LED is on for a whole second and then off for a quarter second. Be advised that there's a maximum frequency which the 555 timer chip can generate. Remember that the frequency of a waveform is the reciprocal of the period, so a maximum frequency corresponds to a minimum period, or shortest period. All the waveforms we've looked at so far have been pretty slow. Let's try something a bit faster. T-on and T-off get smaller as we reduce the values of the resistors or the capacitor. As an example, I'll keep the capacitor at 10 microfarads, but reduce the resistors to 220 ohms and 2K respectively. The formulas tell us that T-off will be 0.014 seconds, or 14 milliseconds, and that T-on will be 0.015 seconds, or 15 milliseconds. The period of the waveform is the sum of the on time and the off time, or 29 milliseconds. The corresponding frequency is the reciprocal of the period, meaning 1 divided by the period, or 34 hertz in this case. I've rewired the resistors on this fourth circuit to show rapid pulsing. I've replaced RA with this 220 ohm resistor. I've replaced RB with this 2K resistor. I've left the capacitor at 10 microfarads. I can see with my eye that this LED is flashing extremely rapidly. I'm not sure that the camera will be able to distinguish between the individual pulses. Remember that a typical movie projector shows 24 frames every second. Movies and videos rely on the slowness of the human eye to merge the individual picture frames into what seems to be smooth motion. 24 frames per second is 24 hertz. This LED is flashing 50% more rapidly than that, at 34 hertz. My point here is that this particular circuit is running as fast as the human eye can see. The 555 timer chip can run much, much faster than the human eye. In fact, it can run about 30,000 times faster. Its maximum frequency is 1 megahertz, or 1 million cycles per second. This corresponds to a period of 1 microsecond, which is 1,000th of a millisecond. Circuits which use the 555 timer chip can also experience problems at the other end of the scale with very long periods. This restriction is not imposed by the chip itself, but by external circumstances. Let me explain why. I've shown here the relevant parts of a 555 timing circuit. Capacitor C is the key. During one part of each cycle, current flows out of the battery and into the capacitor. As the current flows in, the capacitor charges up. The red arrow represents this charging current. During this charging cycle, the red current flows through both resistors RA and RB in series. This part of the cycle corresponds to T-on. Note that the formula for T-on involves the series resistance RA plus RB, which arises because the current must flow through both of the resistors. During the second part of each cycle, capacitor C discharges. The current shown here in blue now flows out of the capacitor, through the chip, and into ground. This current flows only through resistor RB, which is why the formula for T-off only includes resistance RB. Observe that it is pin 7 of the 555 chip which controls when capacitor C discharges. That is why the descriptor for this pin, dis, means discharge. Why does this impose a restriction on long pulses? Here's why. To get longer and longer pulses, the values of the resistors and/or capacitor have to increase. This means that the magnitude of the current which flows through them will get smaller and smaller. As the current gets smaller, it will become more and more sensitive to small fluctuations in the supply voltage, or to small changes in temperature, or even to the drift of values of the components. I experienced this problem even on this simple breadboard. Each time one of these LEDs turns on or off, there's a small fluctuation in the voltage in the power supply rails as the battery compensates for the change in demand for current. These spikes in current and voltage are very small, but they're still large enough to cause these circuits to interfere with each other. I smoothed out the voltage supply using these 100 microfarad capacitors, which I added at the end of each of the rails across the breadboard. Watch what happens to the flashing sequences as I remove these smoothing capacitors. I've taken out 4. Now I'll take out the 4 on the other side. Look at this one for example. It's no longer flashing 2/3 of a second on and 1/3 of a second off. My personal experience has been that the timing of the waveform becomes erratic when one tries to create a square wave with a period of 10 minutes or more. The 555 timer chip is not the best way to go when time periods longer than this are needed. One last thing, the 555 can be used with voltages up to 15 volts. This is very handy because almost all logic circuits are designed to run on voltages less than this. The 555 timer chip can actually operate in 2 different modes. This entire tutorial has described what I call the continuous mode of operation, in which the chip is wired up to generate a continuous stream of pulses in a square wave. To be more precise, this mode is called the astable mode. The A in astable means that the output is not stable. It constantly flips between a positive voltage and 0. There's another mode, which I call the one-shot mode. In this mode, a trigger is sent to the chip's trigger pin, and in response, the chip generates a single pulse. Electrical engineers call this the monostable mode, where the mono means just one. The formulas for this mode are different, and I'll describe them in another tutorial. That's all for now. Thanks for watching. See you next time.